the outline for this is the outline for today's lecture. So we started to talk about green type identity just a little bit. I want to show you what it looks like, because we are going to use it really very frequently in every theorem. And then we will talk about the static regular assumption, which we'll also vaguely discuss, but I will make a rigorous today. And the main purpose of this static regular assumption, in fact, there will be a different type of static regular assumptions when we consider this problem as a general background matrix. But then the purpose of this will imply the kernel will be trivial for the linearized operator. So we'll get into more details about that. And then to handle the infinite dimensional kernel, the standard way is to impose gauge condition, right? So it has been known, but we just reformulate in different ways. There's a elliptic gauge. In our case, we call the static harmonic gauge. But then that gauge is not sufficient to kill out all the kernel. It still have finite dimensional kernel. So we have to think about to solve the problem orthogonally, which we call the orthogonal gauge. And then we'll get to the really an outline of the proof of the existence and local uniqueness theorem, which says on the static regular assumption, we can solve the Bartnik boundary data at suitable conditions. So, so here, this is from yesterday's slide. So I copied down so I don't have to rewrite it again. Let's, for the purpose to, how do we get the green type identity, right? So the very classical functional, really the starting of this ADM formulation of relativity is this one. In the case of time symmetric case where the second fundamental is 0, then the Hamiltonian reduced to this one. So there's a really think about this as a boundary term integral at infinity. And let's give you so-called ADM mass. And then we have this volume integral. And here we think about the input of the functional is a pair of a Riemannian matrix G and the scalar function U. So if we do first variation, so you can think about first variation is you have a starting with a pair, and then you this should be S. And then you do a deformation in the direction of H and V, and then you plug in this functional and you differentiate in S. This is what you get, right? So the key point of this is the boundary term should have a linearization, but it's not there because when we have linearization on the scalar curvature, we actually do integration by part to get adjoining operator. So the integration by part at infinity cancel exactly the linearization of the mass, but then it gives you a boundary term inside. Right, and the boundary term inside does have something really similar to the Bartnik boundary data because this is a linearized level of it. Also, this term here quite ugly, but it's essentially algebraic equivalent to the static vacuum operator. Right. So static vacuum is always a critical point if you consider, for example, H and V is 0 on the boundary, right? The boundary. That's a very good point. So I think even for Euclidean, we don't know it's a stable critical point. With compact perturbation. Compact perturbation, I think yes, but it probably follows from positive mass theorem because the mass is always 0. So, right. I think this kind of related. So we have sort of think about this stability issue, but it's not quite, even for the Ricci flat case, I think stability of a Ricci flat matrix is still, you have to assume some additional assumption. 3-dimension. Yeah, I don't know. So 3-dimension. So for Ricci flat 3-dimension, I think they're more interested in compact manifold, right? Because they will ignore the boundary term for the Ricci flat stability. For 3-dimension, if It's flat, but then you want to say it's stable. I think it's the, right. We will see. We bypass that. Really talk about the concept stability, right? But I think this is a very good point. So I think even my understanding is, I'm not sure about the compact case, but for the Euclidean case, I think it's believed to be stable, but it's degenerate stable. So it's not strictly stable. So I think, right. But I think that's speculated and right. But if anyone know the reference, I'm happy to because definitely that's one of the things we're interested to know about whether those static matrix will be stable, right? I think it will be probably close related to the uniqueness as well. But back here, so this is algebraically equivalent to the static vacuum operator, which I denote by SGU. I will write down the definition for the static operator again. Okay, so of course, this formula will tell you some really intriguing relation to the boundary value problem we are interested in. And one of the things is verified a green type identity. Let me write here, which may be useful regardless of particular this boundary value problem. So let's relate it to second variation, but actually cheat a little bit. Because when you do the second variation, so think about H and V is the first derivative of G, right? If you do the second derivative in S, of course, this you will somehow get the linearized operator. But then you will also have the term which have H V derivative, or that's the G double prime, the two derivative of G and U. And similarly here, and which is usually the information we don't have. Right, so here we are looking at linearized problem, but the formula will involve second variation, second derivative of the quantity which we don't really have information from. So one way to get this is to do the symmetrization argument. So if we consider a two-parameter family, this is I think quite common to get the stability, self-adjoint stability operator. And so if you look at the parameter to be T and S, and here we start with a given pair, and then I do deformation of S direction H and V, and then I do this T and KW, right? And then we take a two derivative, but in the different variables. So this is a scalar value function. So if I do this dt, ds, it has to be, because it will be differentiable in T and S. So you can interchange the order. Right? And then by equating this, you actually cancel out the problematic term, which has a two derivative, which will be a cross derivative, dt, ds, right? Because it's interchangeable as well. So you cancel out last term. So as a result, since we get equality, right? So this is like a first variation. If you do second variation, usually you don't know is equal to something, right? At last you show stability. But then this is get equality, which just tells you self-adjoint property of certain operator. So for the interior operator, you'll be the linearization on this term, which will give us essentially something equivalent to linearized of the static vacuum operator. And I just denote by P. Then you have the boundary term. Sorry, this is P. Before I write boundary term, this is really just tells you you can do integration by part, right? So it tells you put all the derivative into the other term, and then you'll come up with some boundary term. And the boundary term will be the linearization of this. So, and then we will linearization of U and linearization of the second fundamental form, normal derivative, U and the matrix and U. I denote by the operator Q. So let me erase it. So let me check to get the sign correct. So this is the formula, Green type identity. I'm not going to write down what exactly P is, but just remark P will be linearization of this, and this is equivalent, algebraic equivalent to the linearized operator, linearized static vacuum operator. And Q will be some boundary term, some boundary operator. And the key thing is this involves information of the linearized second fundamental form as we see from the first version formula. So we use this identity in many different ways. For example, one thing we really want to know is the kernel of the linearized operator will be trivial, right? So this is algebraic equivalent in the sense like if the kernel of this will be the kernel of that. So we can think about H and V is going to be our kernel element. And for example, the kernel element with the boundary condition, then this term will be 0, right? So we get this term and that term will be 0 just because H and V is in the kernel of our boundary value problem. So we get 2 terms left. And then the one of the thing we use several times is we will plug in test K and W. So which are static vacuum deformation. So in other words, this term for K and W will be 0. So what's left will be this boundary term equals 0. So one test function we use frequently is exactly those one from deformation, from isomorphism group, right? The difference is now we can pick H to X to have arbitrary boundary data. So that gives us some information when we plug in here, because inside it's going to be 0, but it's not the kernel element for L unless we assume X is 0 on the boundary, right? But if we allow X to be arbitrarily, you'll get some information about the boundary value of H and V. And in the lecture 4, when we prove the perturbation theorem results, we actually have to construct more complicated the test K and W to get information from this identity. Okay, so in some way we kind of use the idea of the stability, right? To prove stability, you want to show stability, that you plug in test function to say your critical point has additional property. But here we have no idea whether our critical point is stable or not. But kind of use a similar idea to do the test function to get additional information. Usually we call this kind of hidden boundary condition for H and V by choosing the test K and W. Okay, so we will see one application today already in when we prove the existence theorem. Okay. So now let's move on to the next bullet point is static regular implied trivial kernel. I don't think I really defined what the static regular is. I will do that today. And now for the rest of the lecture today, I will assume we are working on the Euclidean background. Let's make the formula easier. So one, probably let me make a remark later. So just recall the setting. We have the nonlinear boundary value problem. I used the operator I denote by T. So it has the interior operator, which is the static vacuum operator. And then we have the boundary operator, that's the Bartnik boundary data. All right, and the goal was to solve the conjecture. Bartnik conjecture will be equivalent to formulate like you want to give a suitable tau and phi to be the prescribed boundary value, and you want to solve you have to be 0, 0 here. That means it's inside static vacuum, but with this boundary data. And we want to use inverse function type theorem to look at the linearized operator. If we can solve the linearized operator, then we want to say we can solve the nonlinear operator. So the linearized operator, we linearize at the flat Euclidean background. And to know the variation by H and V. So we get the linearized static vacuum operator. So you can see in Euclidean, it's already have some simplification already because Euclidean matrix is also Ricci flat. And so when you linearize here, you get V times Ricci of the flat matrix, which is 0, right? So they have a lot of terms can be simplified. We only have a linearized of Ricci and this one. And the second equation will be the Euclidean Laplace V. So in terms of PDE or analytic point of view, the great difference between the Euclidean background and general background is in fact the second equation. So in the Euclidean case, this equation is decoupled from the previous one. So somehow we know we are looking for really harmonic function on Euclidean space, and that make many things can be simplified. And for the general background, there will be some term here. So we need so that we have the existence and local uniqueness result for general background matrix, but you just make some arguments. You need really new ingredients. And that's because this simple difference, this is not decoupled from the previous equation. Okay. All right, and then we mentioned yesterday, we already know there's an infinite dimensional kernel space to this linearized operator. So if we look at these vectors from the tangent space of our diffeomorphism group. So if it's X, where X is 0 on the boundary, and X is the Euclidean killing, so it will be rotation and translation. right? And then the kernel of L contain everything looks like the lead derivative on the background. And one simplification in the Euclidean case is U bar is exactly 1, it's a constant. So this is also decoupled in the sense we actually have this term to be 0. Okay. All right, so now the static regular assumption is assumption we are trying to formulate will imply the kernel is exactly equal to those trivial elements. So the definition of static regular, we actually have different versions of the names before we coin down this term static regular, because I think it's easier to pronounce it. We have like a non-degenerate condition or a strong vanishing boundary condition and so on, but it turns out we find this term is fancier. So we call this condition static regular. So it turns out to be quite straightforward once we have the setup. So the statement is we say sigma is static regular. So we use the boundary static regular in the exterior. So it's a global condition not only on the surface, but it's a global condition how it sits inside the exterior. If any kernel element satisfy has a stronger boundary condition. So that means if you have any kernel element which have this 0, 0, 0, 0, it actually will satisfy an additional boundary condition. The linearized second fundamental form will be 0, so it will be stronger than the linearized mean curvature to be 0.
Sigma is still the boundary of omega.
Still, sigma is still boundary of omega. Okay.
With this data, compute the operator, identify kernel, or that any H city in the kernel.
Exactly. Right. So if you recall back to the green type identity, I say the green type identity has the boundary operator Q, and the Q involve DAH, right? So in many cases, you want to say if sigma has a very specific geometry like a convex or a certain shape, it turns out we can apply the green type identity to show that this DAH appear in the boundary operator Q must be 0 by using the test K and W.
So this is not just about sigma.
It's global condition.
It's also about omega.
It's also about omega.
Includes our
It's about the exterior. I should say about the exterior. Right. So you should think about it's like probably something like outermost boundary condition is a condition we say on the boundary, but it's actually a global condition.
Say that R minus omega is static regular. That's the object that has a geometry.
Right. But then later we will show that the surfaces, right? What condition of the surfaces? It's easier to say the surface like convex, although convex is kind of local condition, but it turns out it will be static regular just because we have isometry embedded.
So it's actually a condition about our
Yeah.
Together with the boundary. Yeah, it's a condition of iron and with that particular boundary. Okay. Right.
What's the asymptotic sign?
So we want G and U to go to asymptotically flat and U goes to 1. So NG and V will both goes to 0. Okay. So yesterday I found out I probably kind of ignored our online participants. So I got some email questions after the talk. But I think right now I wonder if anyone has any questions, you can post in the chat or just unmute yourself. Right, so and let's move on. So why this will be the condition which will imply the kernel will be trivial, right? Will be equal. So it's actually, it turns out to be already kind of in the literature. It's called the uniqueness of the Cauchy boundary data. So first I have to explain why this boundary condition has anything to do like a Cauchy boundary data. Yes.
So but if we just take that condition, what is EA applied to this LX equals 0?
So this is 0, DA. So that's a trivial condition. Yeah, so it's related to Papitan's question yesterday. Like if you fix the boundary of the diffeomorphism group, why does it fix the boundary condition, right? So it has to compute, but the computation is DAH. The notation is different, but it must be something you have seen before. It's like a linearization of the second fundamental form in the sense you have so like a foliation by some deformation vector x, right? And then you compute if x is the lead derivative. Right, so that means you have a foliation of surfaces starting from this sigma, and you foliate along x direction, and then you get a foliation, and then you compute the mean curvature of lot of the induced matrix. And then this computation will give you like some Hessian of the normal, the lapse, right, plus something, but it will only involve lapse and the tangential part. So in the case x is 0 on the boundary, so this will be 0. So it's all tangential derivative. For example, one thing it does not involve is the normal derivative of nu of eta, which we don't know if it's 0, right? But you only involve tangential derivative of eta and tangential vector. So this condition together will imply, just by taking trace, will imply the linearized mean curvature is 0. So this is Cauchy, can be viewed as a Cauchy boundary data. Because we can always, so now there's already a gauge involved. So if we assume H satisfies so-called geodesic gauge, so geodesic gauge means you can actually choose H to have a special property, such as along one slot to be a normal derivative. This is always 0 on the boundary. And this is called geodesic gauge because that corresponds to you have a deformation of the matrix in the direction of H, right? So you have a family of matrix, and then you can just choose Gaussian coordinates along the boundary. So it also gauge is like a choose coordinates. So you can, for the family of that matrix with the deformation H, then you can choose the matrix to have Gaussian coordinates, and then you linearize it. So if you choose everyone have a Gaussian coordinates and linearize it, you don't have the normal term because the normal part you always normalize it to have distance 1, right? And then the cross term is also not there, so you only get the tangential part. So correspondingly, you say, okay, you just opt to choose a gauge or choose some diffeomorphism such as X. It turns out not only the tangential part of H is 0, but also the normal part is 0, just simply because the geodesic gauge, also the derivative of H is 0 in tangential and normal part. So this recover more the classical way we talk about Cauchy boundary data, because it's going to be a second order PDE on H, but then along the boundary, the value and the first derivative identically 0. Okay, so then that tells you why it's reasonable to expect this kernel will be only the trivial one, because we are looking at the uniqueness of the second order PDE with the Cauchy boundary data. So this theorem has been studied for the Ricci case. So there's for the nonlinear problem, it has been studied by Anderson, Herzlich, and also by Picard. They look at the uniqueness of Einstein matrix with Cauchy boundary data. So if they prescribe the matrix and prescribe the second fundamental form, and inside has to be Einstein, say, with fixed constant, say flat, then the matrix is actually unique. Other matrix is different only in different morphism. So this is a work by they also mentioned Picard's work, and at linearized level, it's been using the similar argument by Zhongshan An, my collaborator. Right, but the argument is very very involved in the sense like this is Cauchy boundary data only when you look at geodesic gauge, right? But the geodesic gauge will not make this elliptic, will not make this PDE elliptic question. So you cannot really just directly apply the elliptic PDE unique continuation. So they actually have to work this so-called H harmonic gauge. I think it's somehow motivated from solving the Cauchy initial data set, Cauchy value problem in space-time, right? You have the H harmonic gauge. They want to choose the slides which have constant or fixed constant mean curvature, and then on each side is harmonic gauge in order to apply that. But fortunately, we are not applying this theorem because we have a more transparent proof because we are in a very specific setting. So I will describe our proof. This PDE, right? So here you are thinking about, suppose we replace this condition by A, because the static regular assumption tells you once we have static regular assumption, then we can replace this by A, right? So we're looking at this boundary value problem, but with this Cauchy boundary data.
So there's no system.
Very good point. So it turns out you need to assume V, but I will say why we don't need to assume V. So if that's a very good point. So this is the system for H and V, right? So the Cauchy boundary data, we need H and gradient H to be 0. Also, we need V 0 and normal derivative V to be 0 in order to say the Cauchy boundary data. But we'll actually see this V and normal derivative V to be 0 will be implied by this condition. That's one of our hidden boundary conditions from green type identity. So that's a very specific thing for Euclidean. In fact, that's the one of the very main reason for when we work on the general static vacuum matrix like Schwarzschild, we have to put the assumption, we have to put the additional assumption V to be 0 on the boundary, and which we call a static regular type 1. But then it turns out this will not enough. We had a hard time to verify hypersurfaces. Any hypersurfaces will satisfy this boundary condition. So we actually have a static regular of type 2, which instead of assuming V, but we put all the assumption on H, we just assume all the normal derivative of A of H has to be 0. And we use analytic, what's the word? Analytic assumption, analyticity assumption to show that. So that's only needed for general background matrix. In Euclidean, there is a lot of simplification exactly because this decoupled phenomenon.
That operator is basically just each knowledge of possible.
Right. So this will be the Linearized operator plus some other term you need to get away second order term by choosing gauge.
You're talking about Cauchy boundary data for this Linearized operator.
For this, right? So it will not be Cauchy boundary data for the Linearized operator because for the Linearized operator you need to assume gauge. But that's roughly the harmonic gauge, or this in our case, it will be a static harmonic gauge version. But you cannot simultaneously prescribe geodesic gauge and harmonic gauge. So that's why in their proof they come out so-called the H harmonic gauge. But that's a very delicate gauge construction. In this case, we can bypass. So this is for the Einstein equation.
Yeah, right. Yeah, that's actually for the Einstein equation. Not for the linearized.
Right. Yeah. So what they do for N does for linearized operator, and she studied the general initial stationary vacuum stationary. So you can look at space time, and space time will be Ricci flat.
So I wasn't sure what when you talk about.
Okay. Right. Yeah. Right. Sorry. Let me finish the theorem. Okay. So here we could possibly quote a result, but I just find it's the whole paper, the result is the whole paper. So in our case, we actually have a much easier elementary proof because we are working on a very special case. And here, let me write down the statement. So the statement is if this equals 0, so in the kernel, and we have the linearized second fundamental form vanish on the boundary, then HV must be the trivial kernel element. So one thing, as Muda already mentioned, like why we don't have a boundary condition on V, right? So it turns out by green type identity, we can actually find out the hidden boundary condition. The hidden boundary condition has different ways rewrite it, but it turns out it will be equivalent to this condition. V, you look at Hessian of V, and then if you plug in the Hessian to be one direction to be normal vector, this is new normal vector, and it has to be 0 on the boundary. So in this case, we can actually do not use green type identity. This hidden boundary condition also comes from directly by restrict interior equation on the boundary, and then you do decomposition, and then you use like a Gauss equation and quadratic equation to rewrite as a quantity on the boundary. But it will be really difficult to explore a lot. Although after we find out we can use green type identity, we found there's another way to do that directly. But I think you'll be clear. It's clear to see why this holds from green type identity. And once we have this boundary condition, remember we are working on harmonic function in Euclidean space. So we can actually show V has to be identically 0. So identically 0 not only on the boundary, but inside in the interior. And the reason is we can take the gradient V will be harmonic. And this condition tells you the gradient V satisfy the Neumann boundary condition. But then gradient V vanish at infinity, so gradient V has to be 0 everywhere. So that implies V has to be linear function. But then V also will show to be 0 at infinity, so the only possibility is V is identically 0. So now once we know this, I think 0, we have the decoupled case. We are working on H satisfy this condition with lot Cauchy boundary data alone. Right. So at that point, we can principally apply the previous result, but we can also show that directly just because our background is Euclidean, right? It's much easier. Yes, please.
Can you explain what you mean by this is unique? Why this is a uniqueness theorem for Cauchy boundary? What is the Cauchy boundary data of an arbitrary HB?
Of arbitrary HB.
Right, you're saying I'm guessing it's uniqueness in the sense that the LXG bar, comma 0 is already. I don't know. Actually, I just really
uniqueness is so this is linear problem, right? Uniqueness will say the kernel will be trivial. But here, because it's a geometric setting, so trivial in the sense it won't be differed by diffeomorphism, right? So it's not trivial in the sense like it's 0, but it's the trivial element. Right, so that's why for the geometry even appear in the rigid flow already, right? So you always have to somehow handle the kernel. So I think Professor Yao just there. I wonder if he can see the previous link, which I have the notes available. Let me just send it to everyone again.
It's not easy to read the blackboard. I try to follow what you said, but not so easy.
Yes, so I have the notes online. I know it's hard.
That will be good.
Right.
Yeah, I try to understand it, but it's not so easy.
I know, right? It's hard. Well, Picanash doesn't catch up. But if you want, I can have a separate discussion with you to present everything. If you just let me know.
Yeah, send me the notes and I will ask you questions. Is Mudao in your list?
Yes.
I can talk with Mudao anyway. So I talk him all the time.
Okay.
Actually, I'm talking to Mudao tomorrow, I think. Okay. Go on. I don't want to stop you.
Okay, thank you. All right. So here we have, so we handle the case of V. So now we are only work the case we have. And H satisfy this boundary condition. And the conclusion is we want to say H is this guy. Right, so we already showed V is identically 0. And the argument with this, because we do the background matrix, we know we have a background Euclidean matrix and it's a complete, it doesn't have inner boundary. So we can first, so we have H defined here. But then this boundary condition enables to extend H globally inside. Extend. So trivially inside. So for example, we can choose the geodesic gauge, and then that will imply the first derivative and second derivative will be 0. So we just trivially extend the 0. So here, geodesic gauge. And then once we get global solution, we show that it's actually a weak solution to this equation globally. And then there's a standard, I think it's a very easy argument. I don't know if it's standard, but it's in our paper. Then once you have a global element, global, right, so you actually have no boundary term appear. So you can, once you have H tilde defined globally, you can just choose the harmonic gauge globally without introduce any boundary, because there's no boundary, right? So there's no fighting between harmonic gauge inside and geodesic gauge on the boundary. We can just choose globally harmonic gauge inside. Yes.
So do you actually assume, I thought you're working in the case when H is a symptotic flat rotation. So H
right.
is 0.
At infinity.
At infinity.
Yes.
So it's not really a it's not really a quotient. It's more like a boundary problem, right? It's not just an initial value. If you impose conditions on the interior and the exterior.
Oh, right. So H has to be 0 at infinity, right? So right, in that sense, that's right. So it will be less strong than those CF references I said, right? They actually have no, it's a local result. They say it's locally trivial. They can patch it to infinity.
So this condition, you do have to assume H vanishes.
That's right. Right. That's right. Exactly. So for our second paper, we use argument kind of like a local theme at infinity. Then if you, I think the problem is when H does not decay, you can still show it will look this form. But then X will not have asymptotic to Euclidean because H determines the decay rate of this, right? But if H doesn't decay fast enough, you can potentially, you could have other, the X, the vector field can have other leading order term. So equivalently, you are looking for solving static vacuum extension, but the matrix is not asymptotic flat at infinity. So if you have some other asymptotics, it's possible you can do, right?
But when you're talking about static regular solutions, you assume H is also
right. Yeah. So
H is equal to 0. Well, approach 0.
Right. Yeah, sorry. So my operator L is defined on the domain where H and V goes to 0 at infinity. But I think potentially this argument could extend to finding static vacuum matrix. I don't know if it's even possible. What do you think? Which is not asymptotic flat at infinity, but with some other asymptotics at infinity. It could be. Definitely, I think probably hyperbolic case will, I don't see any difficulty, although we haven't really thought, we never thought about it. But even some prescribed strange asymptotic at infinity, and you want to find a static vacuum matrix without asymptotics. I don't know if it's possible. I wonder if there is like a probably wild solution. Wild solution could be the one to check, right? Because they don't have, they may not be asymptotic flat, but they have some definite asymptotics, and then you can say finding a static matrix asymptotic to wild solutions asymptotics. So it could be possible. It's a very interesting question. Yeah. Okay. So do you want to take some break? So I think let me finish it and we'll take a break. So once we show this is global solution, then we have, we can use the harmonic gauge for this. We show H2 that must be trivially 0. And then that means H has to be trivially 0. And also this tells us X must be asymptotic to Euclidean. So we finish there and we resume in 5 minutes. Okay. Right, so that's why we put this assumption static regular, because we want the kernel to be exactly those trivial elements. I will just make a remark how what is the difference in the case of a general background matrix. It turns out to be one of the probably one theorem we can prove for the general background matrix, but we really need a lot of new ingredients. And the difficulty is of this argument is because the following two things. And so it's the general, like Schwarzschild background. And the problem first is the manifold is not really complete without boundary. It has boundary, right? So we can only work on where static potential is positive, but then there's a horizon there, so we cannot extend across the horizon. Then we still have to encounter boundary problem. So we cannot use this trick to get rid of the boundary value. But in general, this has boundary. And the second one is the situation will not give you a decoupled equation. So we cannot work on V separately and work con H, because V will not be 0. V in that case will be X on U bar, and U bar for Schwarzschild is not constant, right? So it's always there. So we'll not expect to prove first something this is 0. In fact, it's extremely hard to get hold on the information about static potential, right? So we have to show different U bar for Schwarzschild. U bar for Schwarzschild is the static potential. So it's like 1 minus n over 2r, this one, right? So for Schwarzschild. In fact, if it's constant, it must be Ricci flat. So in any case, the speculating case is we can use the Ricci flat background. And so for the general one, this is not 0. So the equation is highly decoupled. And we don't have a harmonic equation for this one. It's actually decoupled with H as well. So that's why the equation is more difficult to handle. It's a decoupled. Nevertheless, we can show some be stronger boundary condition to get a similar result. So once we show the kernel element must be trivial, what do we proceed next? So before, also we have to introduce elliptic gauge to change the operator L in the interior equation to be an elliptic equation. Let me define some operators. First, the Bianchi for G or any, it can be any, doesn't have to be metric, any symmetric tensor H. This is, so we'll say the Bianchi with respect to the background. So BH is this minus divergence. All right, so trivially, if you plug in G bar to be itself, or everything trivially 0. Right? But then if you plug in other thing, then this equal to 0, usually equivalent to your shown the harmonic gauge. And then we also introduce a killing operator, just define the killing operator. Go back to just easier to write this notation. Right, so then using this operator, we define our gauged operator. So the gauge operator will be this is for the nonlinear. T for my notation is a nonlinear operator. So we have a static vacuum operator. And then we add this gauge term. So this will be input a pair G and U asymptotically flat. And then you define this is the static vacuum operator with some additional term. So without the U there, it really just, for example, if U equals 1, this is really the term to make this linear Schwarzschild operator Laplacian. Right? This is term exactly the extra term. In other words, this is the harmonic gauge. And then for the boundary, we have originally this Bartnik boundary data. Then we also put this gauge term to require the boundary condition. So in fact, without the U, only this is harmonic gauge when U equals 1, right? But then, well, when U is not equal to 1, I think you'll probably find out there's some missing. It doesn't really cancel, right? But because we only care about linearization, when we linearize it, the factor u will not be really relevant.
So killing operators on the vector field or on one pole. Does dgx
dgx.
the killing operator?
Right.
The operator on one pole vector field.
The one form vector field, yes. Right. So this is sorry. Yeah, sorry. Okay. And in fact, so we impose this one just because this term really cancels out the Hessian, and this is the usual harmonic gauge. But it turns out we realize very soon this is exactly our equivalent to a gauge where Anderson Curry they proposed already. So Anderson Curry they study this by looking at the space-time. So they give a really fundamental work to formulate the problem in elliptic, but it's a different formula, slightly different formulation, but it's equivalent. It turns out to be equivalent formulation. So you're looking at the space-time matrix, which is the background is when you do the work product. Right, so you get a Ricci flat matrix. Then you are vacuum, and then they are looking at the space-time Ricci operator with the space-time harmonic gauge. And then this you can think about just the decomposition of the spatial components and the time components. Okay. Right, so you could put u there, but it doesn't matter because when we linearize it, it's going to be linearized of Ricci. U will be 1, so it will be linearized. So how about let me write down the linearized operator. Right, so for the general background, we do have a u somewhere. The formula is more complicated. In fact, to find out the gauge, we really have to go through Anderson Curry's harmonic gauge and then do the decomposition to find out, because the gauge term is quite complicated. It has several other terms there.
Guys, looking at this equation, it doesn't really kill.
Right, yeah. So don't look at this equation, look at the next one. So we really care about linearize, right? So let's look at linearize. So this is the linearized equation. And so probably you feel a bit better because the u factor is not there anymore. So then this is really just a harmonic gauge with the Ricci. Right, so it depends on the background. So this is particular for Euclidean background, this gauge. Okay, so then the lemma is this problem really is elliptic. It's in the sense of Eigenmann, Douglas, Nuremberg with the boundary condition. And that's actually already done in Anderson. So it's exactly the same argument there. Can show this is Fredholm of, so it's elliptic and it's Fredholm of index 0. Also elliptic. If that is elliptic, so you can prove it's Fredholm index 0. And then the second part is some people call this reduced system, right? We call a gauge operator. It turns out finding solution to this will imply the solution to our original equation. So finding solution to this nonlinear gauge operator can imply our gauge operator has the right solution. The second part of the lemma is So this says we solve this elliptic boundary value problem, and we will solve for the inhomogeneous term or the source term to be 0, 0, 0 with this boundary condition to be 0, and then this prescribed. And then it turns out it will give us that solution will also satisfy this one in the sense this gauge will be 0. So now the question is to solve this one. And we are in the elliptic setting, so we have more tools to apply. And one thing about assumption of static regular, the static regular will be able to reduce this infinite dimensional trivial kernel into a finite dimensional one. Okay, so originally we know the kernel of the L, the ungauged operator will look like this. But then with the gauge, you will put some condition. It turns out X must be harmonic vector field. But remember, X is boundary value 0 and then asymptotic to killing at infinity. So that means it has only at most by isomorphism of the Laplace operator. So this has at most finite dimension. The dimension is exactly the dimension of the space of killing vector. And dimension n is the you have rotation vector, which are this many of rotation plus translation. Okay, all right. So now the upshot of we are able to show the existence result is we also find a way to solve the problem orthogonally for the nonlinear problem. So in this notation, we can decompose for the linear operator, gauge linear operator. Now we know it's fraction of index 0, and we know what kernel exactly is this n-dimensional guy. So we have the complement of the kernel. Right? And then, but we know it's fraction of index 0. So we also have a range of LG plus the co-kernel. Co-kernel will be something, let me call I think I use Q. I hope you don't get confused with the operator. This both Q. But Q has also dimension. This is the complement of range of LG, but it also has dimension n, right? So this dimension n, because it's fraction of index 0. And this epsilon space is the one complement to the kernel of LG. So we just pick the one which is orthogonal to it. Let me give a name to this space, to this vector space to be gauged vector space. So this is our orthogonal gauge. So we say G, U satisfy orthogonal gauge really is just a condition on G. So in other words, G minus the background is orthogonal to those guys in the gauge trivial kernel. So then this, once we already have decomposition for linear operator. So for linear operator, it's actually, there's a standard way to solve orthogonally, right? But the thing is we can solve this in a suitable way for the nonlinear operator as well. But let me write down what the statement we have for the existence and local uniqueness. So we will, let me make a remark. The nonlinear operator so we get this. So that's our assumption. The boundary is static regular in the exterior. And then is the existence result. So under the condition, the boundary hypersurface is static regular. Then this is followed from the inverse type function argument, right? So you can, there's constants epsilon 0 and c, such that for any epsilon in like a less than log constant epsilon 0, and for any pair of symmetric tensor and function, such as sufficiently close to the induced Bartnik boundary data on sigma, then we can find the static vacuum extension G and U. From our construction, you will be also close to the background, which is the Euclidean pair. Realize that boundary data. And the solution is locally unique in the sense okay, so in terms of, so this is, if it's a PD question, then of course you get different solution as tensors, right? But they're geometrically unique in the sense, all those different pair of tensors and function, they're only differed by diffeomorphism. So we can do that in the neighborhood of it. And more precisely, we know you can, if you fix the static harmonic gauge, orthogonal gauge, there is a unique one. So in this sense, there exists So any pair, regardless static vacuum, regardless solution or not, well, there's always a unique one in the orbit of diffeomorphism group satisfy both the static harmonic gauge and orthogonal gauge. In particular, for solution, we find out. And there's a unique one in the orbit, and that's the one that satisfy both gauge. Yeah, I just realized I never really defined static harmonic gauge, right? So static harmonic gauge will be the one with the gauge term 0. Sorry about that. And without U there, it's the traditional harmonic gauge. So but we put the static there to say there's a term there. All right, so so the construction, I think I will probably get in a bit details, but it's actually it's like the theorem we spend less time to prove because somehow there's all the puzzles just fit together nicely. So once we can solve the linear operator orthogonally, and remember the variational feature tells us there is some orthogonal decomposition for the nonlinear operator as well. So that's just my first variation of it. And that's in the yesterday's lecture, that's the first consequence from the variational method. So there's an orthogonal decomposition for the nonlinear operator as well. So that helps us to solve the problem orthogonally for the nonlinear one. Okay. Right, so I think that will be all for today. So once we have the existence and local uniqueness for the lecture tomorrow and the last day, we'll say to verify there are a large class of hypersurfaces in Rn or in general in the background static vacuum matrix like Schwarzschild. There's a large class of sigma which are static regular. So that boils down the problem to verify this analytic geometric condition. Once we show the hypersurface is static regular and the existence follows. Okay, so I stop here for questions.
Space xg, the one you just erased.
HG, XG, yes.
Right. So I guess your x star with those vector field that are 0 is and that well, that approach to
Euclidean vector killing.
one of coordinate functions.
Euclidean killing vector. So there will be translation. They will asymptotic to constant vector or rotation.
Or rotation.
Right.
And then, but then you pick up this condition of not passing 0.
Right. By
right. You kill the I mean the dimension used to find that.
That's right.
Just the isometry.
That's right. Right. And the one thing missing, so we saw that this result was proven in the literature already. So, but it turns out it's not because there is some confusion about, because in the case for compact manifold without with boundary, so even for compact manifold with boundary, if there's no infinity, then the static harmonic gauge alone will make the kernel trivial, because it looks like in this case you will be looking for vector field which has 0 boundary value on the boundary harmonic function, right? Which it must be trivial. So then in the past literature, I think we feel like they are assuming so we're assuming more correct boundary condition at infinity. So we cannot really assume, we cannot just restrict the class to be even H has decay, but the kernel may not be decay, right? So I think that's one confusing point in the past literature, because you have necessarily considered those killing vector field, because there are the diffeomorphism which preserve the structure at infinity, which is already identified in Bartnik's paper in 78, right? So if you say, okay, I'm looking at, even for a linearized problem, it'll be easier. You say, I just restrict this vector field to say decay to 0 at infinity, but that will not help you to solve the nonlinear problem. So we have to really overcome this finite dimensional kernel. It's not trivial. If it's trivial, the inverse function theorem just follow. But the thing is not trivial. Nevertheless, it's finite dimensional, so it can be handled.
Any questions on Zoom? You'll go through TG orthogonally and
Right, I feel I can do that. We can do that privately. I was planning to do that, but it turns out I don't think I have enough time. It's a bit technical to do that in the last 5 minutes, but we can talk about that if you're interested.
Sure.
Right. I think if you don't know what I'm doing, it will be very difficult part of reading in the paper. But I think, right, but it just comes from, I think there's a more, I don't know, we solve it like a shorter amount of time. It's just everything we just put together nicely, right?
oh, there are no more
Okay.
questions.
All right, thank you. Thank you all for coming.